All right, here we are. Well, thank you all for coming. This is the Catalyst webinar. Hopefully you or found yourself in the right place. We're going to start off with a bit of an introduction from Berk on what Kitware is, and then we're going to dive into the content. So, anyway, thank you so much, Berk. Take it away.
Thanks, Corey. Hi, everyone. I'm Berk Geveci, and I lead the scientific computing team here at Kitware. So today we're going to introduce Catalyst and ParaView Catalyst. These are our open source platforms for delivering in situ analysis and visualization. So I will, at the beginning, I will start just to have a short introduction to Kitware, and after that, Corey and Christos are going to take over, and they'll cover the technical content. So they'll start with a high-level overview of what in situ analysis is. Then they will delve into some of the Catalyst details and introduce how to use Catalyst, and then they will wrap up with some applications. So during the webinar, we're going to take short breaks to answer questions. So if you have questions, there is a chat interface in my UI, it's on the upper right, where you can type questions, and then I will monitor those, and throughout the webinar, I will interrupt Corey or Christos read the questions to them. We will also stop for a few questionnaires. And Corey will, I'm sure when we get to the first one, Corey will introduce that. So just a brief introduction to Kitware. So Kitware is a leader in scientific software in AI research and development. We work with government agencies, industry, and academic institutions to handle complex problems in computer vision, medical imaging, scientific computing, and high-performance software systems. And our mission is to essentially build cutting-edge open source tools that accelerate discovery and to empower innovation. Our team includes over 150 engineers, researchers, and developers, and we're spread across 6 offices in the US and Europe, including New York, where I'm located, North Carolina, New Mexico, Virginia, Minnesota, and Lyon, France. So this distributed collaborative cultures helps us deliver impactful solutions on a global scale. At the heart of Kitware's philosophy is our deep commitment to open source. We believe in building sustainable platforms that bring communities together, platforms like Tram, ParaView, and today's Spotlight Catalyst. These tools don't just solve problems, they encourage collaboration, accelerate progress, and form the foundation for the next generation of innovations. So if you can move to the next slide, Corey. So as I mentioned in the previous slide, we're a highly collaborative company. Our largest research efforts are generally funded by the US federal government and involve many commercial and academic partners. We're also involved in many smaller research efforts. We perform custom application development, and we also provide support and training on our open source platforms. Our areas of expertise span energy and manufacturing, with a focus on simulation workflows, high-performance computing, scientific visualization, and data analysis. We also work in healthcare and life sciences with a focus on digital pathology, surgical planning, medical image analysis, medical visualization, and bioinformatics. And for our defense and intelligence customers, we work in visualization, data analytics, image and video forensics, threat detection, and activity recognition. Deep learning is also a large part of what we do, and we have a strong emphasis on ethical and explainable AI. By the way, I don't know if you can hear that in the background. There is a fire alarm testing going on here. So now that we have briefly covered who Kitware is, I'm going to introduce Corey and Christos. They are the 2 leading developers of Catalyst, and they're going to continue. But before I hand it off to them, I'm going to mention that during the webinar, we're going to take short breaks, for those that did not hear this, to answer questions. So if you have questions, enter them in the chat interface, which is, in my case, on the upper right, and we will try to answer them throughout the webinar. I'll interrupt Corey or Christos and ask them the questions. We will also stop for a few questionnaires that Corey will introduce when the time comes. So that's the introduction, and Corey, please take it away.
All right, thank you so much for that, Berk. So yeah, we're going to start off talking about what in situ analysis is for the uninitiated, and hopefully we'll get a sense for who here has some experience and who here is new to the field. And then we'll kind of move on to talk about catalysts and its use cases as the talk continues. So to get us kicked off, I have one of those poll questions. So what in situ analysis platforms do you use in your simulation workflows? And if you don't use any yet, let us know. All right, looks like we have our results in. Okay, so it looks like roughly half of you have not used in situ analysis in your simulation workflows today. So maybe today we're going to be able to convince you to try it out. I see a lot of Catalyst 2.0 users here today. That's fantastic. And I see we have 5 folks who are using something else, which is exciting because I'm curious to hear, what the lay of the land is here in this in situ analysis ecosystem. But all right, let's get into what in situ analysis is and what we can do with it, focusing on Catalyst. All right, what is in situ analysis? So in situ analysis or visualization is a workflow that kind of is a response to the growing I/O bottleneck, which is experienced when a simulation running on very, very large, massive computational scales tries to write significant data to disk. The traditional workflow of periodically writing data in the form of restart files or temporary files, etc., can become like totally untenable as the size of simulation data increases. We desire often in traditional workflows to write data to disk and then bring that into some sort of analysis or visualization platform, such as ParaView. After the fact, we refer to this as sort of post hoc analysis. This can end up not only creating a significant overhead for your simulation to write out large data to disk, but also increases the amount of time the user must take to then perform the post-processing after the fact. In situ refers to workflows where analysis and visualization tasks are performed alongside the simulation. That is workflows where tasks of visualizing your data or post-processing your data actually happen on the same computational resource on node using the same memory spaces as your simulation. We refer to this as sort of a zero copy architecture where we can actually represent your data in the simulation without moving it around for the task of visualization and analysis. We'll also talk a little bit about what are called in-transit workflows. And this is a related sort of workflow in this ecosystem where data can be shuttled from your simulation to a fully separate compute resource, typically some sort of visualization cluster, where users can then interact with their data in an asynchronous manner while it is being produced. This also cuts down on I/O, obviously at the cost of network operations. So let's continue forward. There are a ton of benefits to using in situ workflows. I think I've hinted at sort of the major ones, minimizing the I/O bottleneck and getting results faster. But let's kind of walk through some of these in order of complexity. So first off, quick and easy runtime checks. Typical simulations do provide some sort of diagnostic as they're running. That's pretty par for the course, often written to log files, or maybe you have some sort of dashboard that can track convergence rates, etc. And that's fine. But we can do more with access to directly being able to render your data. Being able to directly output images from your simulation can identify incorrect behavior much faster than, say, a convergence plot. Additional analysis for identifying divergence or undesired or even just simply incorrect configurations. Say you miss a minus sign, or you added an extra zero to your input to your inlet velocity. These things are it might not lead to a broken simulation, but that's going to be an incorrect sort of configuration, which is much easier to catch when you have rich visual data to diagnose these issues with. Further, this sort of computational monitoring can be tied back to your simulation for what we've referred to as computational steering, where we can combine sort of compute and human input directly. Say you have access to solver parameters that you care about monitoring, being able to actually affect those can save an entire run if you are able to change them in situ. So next we have access to full simulation data instead of what is simply economical to save to disk. Say you have a simulation running at very, very large scales. Say you had access to the Frontier supercomputer at Oak Ridge. You're able to produce massive, massive amounts of data with these simulations at very high computational rates. But saving that data to disk can, it can blow your disk allocation very quickly if you're not careful. And so having access to the full simulation data as it's in memory while it's being produced can give us access to that data faster. This leads to more data that you can process at once, which can be necessary for better insight. First, finally, we have faster time to insight because we're not wasting time with writing large data to disk and then bringing that data back out for analysis, missing however many time steps we needed to miss in order to stay within our disk allocation. We can get better faster. We can get better insight faster. And this is certainly true for configurations because I/O can be a significant cost for running a simulation, where writing, say, images to disk or some sort of small data extracts that can be analyzed further can be significantly cheaper and get you answers faster. And this can also increase your rate of post-processing as well. Because we have access to your full simulation data, in-situ tools can be used to parse down that data into manageable collections of data for further insight down the road. So we can sort of combine the best of the exploratory post-hoc workflow with in-situ's great cost savings and computational efficiency together. And finally, we get to use the HPC systems as efficiently as possible. We don't want to be leaving computational resources to fallow when we have limited allocations. And so we can take advantage of more computational resources when we perform in situ analysis rather than trying to analyze our data in a post hoc manner. This can replace slow file IO operations, for instance. If you're writing files to disk, you're not performing any kind of analysis or visualization. And so that's not necessarily flops that you want to be using if you can avoid it. But further, for heterogeneous systems, which are sort of the name of the game in HPC, where we have massive computations happening on GPUs, we can take advantage of more of that system by using underutilized resources. For instance, if you have a very high performance GPU-based simulation code, being able to use CPUs that are there and actually perform computations across the node that you have an allocation for can greatly saturate your allocation and perform more computation for the allocation that you're given. And that's where Catalyst comes in. So Catalyst has kind of led the in-situ computing since the beginning. This is a production-ready software where we bring the full suite. We're going to mostly be talking about ParaView capabilities, bringing the full suite of ParaView capabilities directly to your simulation. ParaView being a massively parallel HPC-first visualization and analysis tool that I will say is open source. It's pretty cool. Go download it if you haven't. And this is able to scale to gigantic scales. Catalyst has been recorded running on the Frontier supercomputer at Oak Ridge National Lab, at the time the largest supercomputer in the world. But this is scaled to over 1 million MPI ranks. So we're talking gigantic data can be processed with Catalyst in situ. And this is great because we can be flexible and we can scale to, we can have confidence that we can provide insight. We can increase your time to insight no matter what scale you're operating at. It has been nominated and has won many visualization awards. including a number of Editor's Choice Awards in its early days, uh, as well as Reader's Choice Awards, where it actually tied with ParaView, as I said, one of the core engines of Catalyst. So this is pretty exciting stuff that ParaView has been recognized for. And of course, as I said, this is used on HPC architectures. If you have access to large compute services, this is the type of tool that will get the most out of that allocation. All right. So I guess before we move on to the next section, I just want to pause for half a second to make sure that we have time to let questions go through it. I don't know if we have any currently recorded, but if you have any questions so far, happy to pause here for just a moment. I have no idea how to use this GoToWebinar functionality, so if there are questions, let me know. But otherwise,
I will let you know if there are questions. There are not any right now.
All right, perfect. Thanks, Berk. All right, so we're going to move on then to how Catalyst speaks your language. The goal of Catalyst is to kind of stay out of your way while providing as much insight as much access to insight as possible. Catalyst travels light. We like to think of it as an easy to deploy, develop, and maintain API. To start, in order to accomplish deployment, the Catalyst library has no external dependencies. So when you actually go to build a simulation that's integrated with Catalyst, you only have to link against a small Catalyst library. And this obviously does not bring all of the functionality that ParaView brings, but that happens at runtime, where we actually link to a runtime library dynamically, so that you don't have to go through the admittedly arduous process of bringing large-scale visualization libraries into your simulation suite. This is often not something that you want to be doing, and so being able to do that at runtime and make selections of the types of tools that you want is super critical to this sort of architecture. The API for Catalyst is really 3 methods, and 5 if you're fancy. We'll get into that on the next slide. So as I said, this is trying to stay out of the way of your code. We want to make this as straightforward as possible to integrate, and then get access to all of the visualization tools as quickly and easily as possible for the users and developers. Finally, the API is stable. So this is important for maintenance, but it's also important for the architecture that Catalyst provides you. So as I said, we have 3 methods, and the goal is to keep that stable for all time, as long as possible. I don't know. The future is a scary place, but we have access to. Our goal is to kind of match what is called an ABI compatibility, which is popularized by, for instance, the MPitch library, where libraries can attach themselves to implementations at runtime. And so that's how Catalyst works as well. And in order to accomplish that, we have a stable API that won't change underneath your simulation, but we can change out the implementation of Catalyst so that you have access to new features as they're developed. Now let's talk about that API. Like I said, there's really 3 methods within the Catalyst API. We have an initialize, an execute, and a finalize. Initialize and finalize happen once during your simulation. One sets up pipelines, connects to that back end for you, as well as allows you to pass in various runtime parameters. Finalize similarly cleans up pipelines at the end of your simulation run. Catalyst execute is really where all of the work happens. This is something that you can call every time step within your simulation, and this takes a description of your data as it is in memory and passes that along to a Catalyst pipeline. And this is, and then within that Catalyst pipeline that is user specifiable, and we'll get to that later in this presentation, you'll be able to actually perform analysis and visualization without actually copying your data. It's simply a description is passed from your simulation to the pipeline. Like I said, 5 if you're fancy, we have also a Catalyst results and a Catalyst about method. The results is a very interesting, powerful command where you can actually return information or data or parameters from the Catalyst pipeline to your simulation. And it's this that enables computational steering, where users can pass in user modifiable data back to their simulation to change things about the simulation runtime. Catalyst about is simple at its outset, but I think has some really interesting kind of texture to it. So Catalyst about simply returns information about the implementation of Catalyst that you have linked to at runtime. And this information might not be useful to everybody, but if you have access to many different Catalyst backends, understanding how your simulations should respond to those particular backends could be very important and provide a lot of flexibility within your simulation workflow. All right, so now I want to open up the next poll question.
Hey, before you do that, Corey, there is a question.
Absolutely. Oh, perfect.
That says, do you have to call Catalyst execute every time step?
You do not. You can. It's flexible enough to do that. And there's a number of different ways to specify when the pipeline is actually run. If you want to manage the cadence that you call Catalyst execute from your simulation, that's totally fine. But you can also manage the execution of pipelines, the cadence of that execution from within your pipeline scripts. So this is kind of one of those pieces of flexibility where you do not have to call Catalyst execute every time step, because Catalyst execute can also, your Catalyst pipelines can also provide that sort of cadence as well. So, thank you for your question.
One more question.
Wonderful.
What is the bandwidth for Catalyst results? Is there some limitation on how much data can be transferred? I'm thinking about digital twinning.
That's really interesting. I think that the bandwidth is going to be really specific to your problem. This because the pipelines in sort of the traditional way of running this run on the same hardware that your simulation is running on. You are limited by whatever sort of memory you have access to on your particular compute node. But if you want to pass very, very large data back to your simulation, that's totally fine. Even data on the order of the size of your mesh, for instance, is something that can be handed back if you have the memory bandwidth for that specifically on your machine.
Yeah, one more question.
Right. Oh, fantastic.
And that is, I wonder if Catalyst results is designed to interact with virtual reality.
Designed to interact with virtual reality. That is a fantastic question. We have not demonstrated such a capability. However, ParaView as a visualization platform does have VR rendering capabilities. And so I would love to investigate how VR could be incorporated into this particular sort of schema. Since we have ParaView sort of as a core engine for Catalyst, maybe it would be, I'm not going to say straightforward. I've never worked with VR before, but it sounds like something that's very promising. I think that would be awesome to try out.
Yeah, I do want to add a quick thing to that is we're covering the sort of the bare bones of Catalyst here. Essentially, you have the ability to construct more complicated workflows, especially if you couple with what we call in transit, which Corey mentioned that, where you can actually have asynchronous jobs running that are then communicating with the simulation. VR would be a good example of that. So I wonder if there's a lot of questions coming. Maybe we do the poll and go a little bit further, and then meanwhile I will digest the questions and see if I can get them all.
All right, phenomenal. All right, so let's get to that poll. I just want to know what programming languages are being used by this audience. I'm very curious about that overlap between what Catalyst supports as well as what you all are using. Incredible. We've got a very large showing for C++ and Python. That was pretty expected. We have one person on Rust. That's exciting. Okay. And we've got others as well. I know the coverage of programming languages in this poll is pretty weak, but I think these are the big ones that you hit in scientific computing. So, all right, phenomenal. So it looks like we got everybody here. Yeah, 85% C, C++, that tracks. Python is also very big. Happy to see a few people still chugging away at Fortran. I do that when my arm gets twisted. We have two people on Rust, which is very fun, and a couple people on other as well. All right, do we want to ask another question?
I got some more questions.
Perfect.
One that you like, Corey,
Okay,
and that is it possible to access GPU memory and pass it via Catalyst or only CPU?
that is correct. Yes. So if you have GPU resident
That
simulation
is
memory,
correct. Being it is possible, right?
it is possible. Yes. Yes, if you have a simulation running on GPUs, you can pass that along as array handles, as device handles to Catalyst without copying them. And then those device handles will, uh, you will have to have a GPU ready script, Python or Catalyst pipeline, but we use VTKM for that.
And an important question, once Catalyst is embedded to my system, can crashes or bugs in the visualization pipeline bring down the simulation?
It depends. Various warnings and errors are handled via VTK and ParaView's error handling. Particular like out of memory seg faults, etc. They can cause issues, but fortunately we rely on the VTK and ParaView very robust CI infrastructure to catch these bugs as they come up. And we also have, if you do find these, which happens all the time with very complicated systems, we have a pretty robust issue tracking system that you are totally free to report these to.
One other thing I want to add, if you have a use case where you absolutely must isolate the two, the only solution really would be to use some sort of decoupled system like in transit, like Corey mentioned before. In that case, especially if you're using Adios that has a publisher subscriber architecture, where if the process that's pulling in data from the simulation dies, your simulation will continue to function. Okay, there are more
Absolutely.
questions, but let's keep going.
Okay, perfect. So, unfortunately for you two Rust users, we support C, C++, Python, and Fortran natively out of the box with Catalyst. If you are really interested in working with Rust, let me know. I think that's awesome to see other people using other tools, and especially programming languages here in the HPC space. But we wanted to cover, obviously, we have great coverage, I think, for these really popular, really powerful languages here in HPC. And these are pretty straightforward to use as well. The API is shared across C++, Python, and Fortran in a fairly natural way. So Catalyst further is clever enough to run pretty much anywhere, I think, certainly from laptops all the way to supercomputers. It supports macOS, Windows, and Linux. So if you are a Mac developer like myself, it is very straightforward to run Catalyst locally before moving on to your very, very large clusters where it's going to get the most. We're going to have the most horsepower to run these sort of analysis pipelines. It runs all over the place. Getting back to that question, GPUs or CPUs or combinations of both are feasible with Catalyst as well. And so it's pretty exciting that we are able to support sort of, the highest level of computing. It's like exascale world that we're finding ourselves in right now. All right, so now we've got a demo coming up that will be run by Christos here. Before we go on to that, do we want to try to get through a couple more of the questions?
Sorry, I'm responding some of the questions online on the interface.
No problem.
Let's keep going, and I'll. So far, I haven't. Oh, somebody said surprising to see, not see CUDA as a language, but I think we already answered that there is direct GPU support, and that does include what VTKM/VSCORE supports. So that means CUDA, HIP, and SICL.
Yep. Awesome. Yeah, that's right. I guess I think a lot of applications are built in C++ and use CUDA as sort of the GPU kernel, and device pointers passed from CUDA can be handled natively with Catalyst. All right, so here we go. Let's see if we can get this running. All right, take it away, Christos.
Yep, so in this simulation, we start with loading a core solution, which is very common when you do this kind of preparation of scripts. And this is a hydrodynamic simulation coming from LULES, from the Lawrence Livermore National Lab. And we are interested in this region that you see here, which is an expanding shock traveling through the domain, starting from the lower corner. So what we do is we start by adding some ParaView filters. We add the celled point data, and then we create a contour filter on top of that, because, and on this specific variable, because we know that this is of interest, it's on the cusp of the shock. So that's something we want. And now what we want to do is to do exactly the same steps at every iteration of the simulation. So what you do is we go and add an extractor, and we have this VDPT file, which is just a VTK file. And as you see, there is frequency there, and you can control when it starts, how often it will run, and all of this. Now, next, we want to do something more, and to visualize this wave as it travels through the domain in a different way. And we will use the plot over line filter. And you see there is like lots of variables there, so we will clean this up a little bit and keep only the velocity. So what we want to see is this wave traveling from left to right. We can also add live data, like the time that this simulation is, and then we make sure that it's selected. And what we will do is we will add yet another extractor, and this time it will be a PNG, so you have this nice graph produced for you at every iteration. And then, of course, there is the actual raw data, not only the figures. So you can actually also extract those via a CSV now extractor that gives you the raw data at each iteration again. And then finally, because we have this nice 3D view, we want to take a screenshot of that at exactly this point of the camera. So yet another extractor, a PNG, and that's all that we have. So to recap, we have one screenshot for the 3D view, one screenshot for the 2D view. We have the CSV, which is the raw data for all the variables, and then we have this VTK file, which is the contour that I show you. So once everything is ready, you go and extract this as a catalyst state. And again, you can configure things like when it will run and how often and all of that. I will go for the defaults for now. And I say that I go back to my simulation, which uses this script, and I let it run for a few iterations. You can see live that I have all these files popping up. And at some point, I will stop the simulation so we can look into these files. So first, we see the 2D graph. Velocity initially is 0, but then we see this graph that starts from the left and moves as the wave moves through the domain. So that's really cool. And then the other screenshot that we have further below is the render view. So this is the 3D view. And you can see that, first of all, notice that it's a more dense domain, because I started with a coarse data set, but now I'm using the full. And you can see the wave starting to evolve from the lower corner. And then I also have this CSV file, which is just a dump of all the values. You can post-process them, use them in tables or whatever you need. And then there is all these contour values, which I will switch back to ParaView to show how we can visualize them. First, I will clear everything that I have. And then you can add the actual files at the time series, so you can see them how they play through time. So I go to the data sets, I select all of them, and then I tweak my time to start and color it. And then once I hit the play, you will see that this small wave, it starts to move through time. And of course, you can do way more, impressive things like that. That was just a quick example for you guys.
So I have a question.
Fantastic.
the question says, how do you save both views using a single PNG extractor? This is equivalent to save screenshot, but that would not make it into the Catalyst state.
So when you create an extractor, you select which view you want to extract, and that way it will pick up the correct one. So it's in the video happens quickly. We have this video on YouTube with subtitles, so you can see it carefully that I select first the view, and then I create the extractor, the 2D view, and then I select again the 3D view, make it active, and then select the extractor. So this can handle multiple, and you can have even many 3D views. Nobody says that you need to constrain yourself in one.
So you have to then construct them yourself afterwards.
Mm-hmm.
Another question, are there examples of containerized deployments with Catalyst?
Phenomenal question. We do not deploy containerized ParaView distributions directly. However, I am aware of some floating around the internet, and I've including one that I created for a workshop a little while ago. This is something that we maintain directly. If that's something that you're interested in, I'd be happy to hear more about your particular use cases.
One thing I want to add, that's why actually, I don't know if people noticed I walked out. I went next door to ask a question. We distribute the Catalyst implementation on our Linux binaries. So those binaries, I mean, this is for evaluation purposes, right? If you're running it on a cluster, you need to really compile it for that cluster and stuff like that. But the compiling against the simulation itself is a very simple process, right? That is not a difficult thing. If you do that on Linux, you can actually point that to the Catalyst distribution that's in ParaView. The ParaView binary that you download, and we'll have that support in the future for other distributions too.
That's great. Yes, thank you so much for that demo, Chris, as well. That was really phenomenal. So I wanted to kind of point out a couple things from that demo. One, in order to produce that pipeline that the simulation Lulish ended up running in situ, Christoph didn't write any code. So all of that was produced in ParaView using the graphical user interface, using a kind of dummy simulation data as a stand-in for the high-resolution simulation data that would be computed later. And so that's really powerful, especially for users who don't necessarily want to have to fiddle with significant visualization code. It can all be done directly in ParaView, and the images that you get are going to match those that you would produce in ParaView. Oops. Here we go. All right, so now that we've kind of worked through what Catalyst is, what in situ analysis is, what Catalyst is, and how you actually can use Catalyst directly in your workflows, I wanted to sort of go over some of the cool things that you can do with Catalyst and actually to make your simulations smarter. So are there any other questions before we want to move on? Are we good to go? All right, let's move on. All right, so to start, I wanted to show off I wanted to illustrate sort of the initial sort of idea for doing in situ. The kind of raw thing that you are capable of doing here is having high frequency renderings. So the video in the middle might be a little choppy depending on the network connection, et cetera. But I wanted to sort of visualize how post-hoc rendering versus in situ rendering is really a big game changer. So if you have very large data that you have to write to disk in order to visualize, you're only going to be able to write so many frames, so many time steps before you're going to blow your entire hard drive budget. But with in situ, you have access to every single time step. And so at any cadence you want, you can write out images. So you can get the same video using the same renderers, the same sort of techniques, ray tracing, whatever you want, but at a much higher frame rate. And so you can actually produce lovely, buttery smooth videos of your simulation directly as your simulation is running. And so as soon as it's done, you can have access to all of these frames without having to write your entire simulation to disk at this sort of rate. So here I think we have like, I think it's like 16 frames per post hoc frame out of in situ for this particular example here. But there's more that you can do with this. So not only can you write images, but as Christo showed, you can actually write data extracts. So he had a system of writing contours, and you can take that sort of technique and produce even more insight with the data that your simulation is producing. Just through the concept of data extracts. So here's an example of a very large scale contour around a helicopter. Catalyst can partially process simulation data and then write those processed data to disk for you to then explore later. This can be done at whatever cadence you want as well. Because this is significantly reduced from your simulation data set, it's much more manageable for a user to actually perform sort of exploratory analysis and visualization. This can lead to some really interesting sort of issues, but Catalyst actually can handle a lot of the sort of I/O bottleneck that comes with writing, a lot of files to disk as well. So here we can actually take your contour, for instance, that is spread across, say, 1,000 domains on your HPC system. Some of those domains are going to have no actual data to contribute to that contour. And some will have very little, and some will have a lot. But that can lead to some inefficiencies, and we actually have capabilities to directly reload balance that data and write many fewer files to disk. So that, again, in the spirit of reducing the actual amount of overhead for getting to insight as possible. I think this is a pretty powerful technique that we have access to directly with Catalyst and through ParaView. But there's more to Catalyst than just ParaView Catalyst. There's actually, because of our infrastructure for dynamically loading implementations of Catalyst at runtime, you implement your code with Catalyst one time, and now you have access to an entire library of capabilities. We've been talking about ParaView Catalyst here for most of this talk, but we actually have access to other implementations, such as Ascent or Adios, which we'll talk about next. So Ascent, for those of you familiar, and maybe we want to pause if there are any Ascent aficionados here. I think I saw a few of you in the first poll. Ascent is a very powerful visualization and analysis tool. It has quite a bit of overlap with the functionality of ParaView, but it's really meant to be as lightweight and small as possible. And it uses what's called actions to produce workflows. So you can actually put together these sort of YAML-based, human-readable action pipelines that are triggered via sort of naturally readable triggers based on your data or other sort of parameters, etc. It's heavily accelerated based on the VizCore's library. And so it kind of brings a lot of interesting and powerful visualization tools to the mix. And it really, I think of it as a sister to Catalyst, but with Catalyst, we actually have access to it as well. So you don't need to implement a Catalyst adapter and an Ascent adapter in order to get all of the functionality you want. You can have it right out of the box with Catalyst as well. Next up, we have Adios. And I think Berk mentioned this, Berk talked a little bit about this earlier, but Adios actually provides a very efficient methodology for transmitting data from your simulation to a separate compute resource. So here we have an example of how you can reduce the total compute time for your simulation by copying and sending and streaming your simulation data to a visualization cluster for performing more user-friendly, exploratory sort of analysis and visualization asynchronously from the runtime of your simulation. I think it's a very powerful tool. Berk, I don't know if you wanted to say anything else about this tool before we moved on.
Sorry, I'm busy typing answers to questions.
Oh, that's fantastic. I'm glad to hear there's so many questions. That's great.
By the way, when you have a natural breaking point, there are some questions.
Okay. Well, I think we might be getting to the next poll question, so maybe we want to pause here and hit a couple of those questions.
Okay, so this is a question that I'm still trying to wrap my brain around. It says, synchronization. Can a fast simulation back up? How can PV acknowledge it's ready for the next step?
can a simulation back up? So out of the box, Catalyst isn't specifically set up with a memory. So it's not going to remember past time steps, for instance, unless you ask for them explicitly, and there's only a few mechanisms for doing that explicitly. So if you have a very fast simulation and you're trying to, say, do this sort of in-transit analysis where you're sending data very, very quickly to some sort of interactive environment, there might be some contention. You might be getting data faster than you'd like. And I think that we would need to look at sort of the specifics of your implementation. However, if you have access to a live connection to ParaView, for instance, we do have sort of out of the box a pause mechanism where you can pause a simulation if you're moving too quickly through that, like through your time steps, for instance. I'm not sure if hopefully that answered part of your question.
Yeah, I want to quickly add something. Again, we're covering here sort of the basic use cases. So one of the things, for example, we're considering for one of the use cases with one of our customers is to run the actual compute of Catalyst in a separate thread. The idea being that the simulation is actually running on the GPU and fully leveraging the GPU. The CPU is mostly idle. And so we actually want to not use the GPU, run in a background thread, and use the CPU and pay the cost of course, the GPU to CPU data transfer. In that particular case, this situation of simulation backing up can totally happen. It could also happen in the in-transit use case that Corey just covered in these. There is not a lot of built-in mechanisms at this point to handle those workflows. You have to build that to your code, meaning the code, whether it's in Python or whatever you're implementing it. But that kind of takes me a little bit to another question, and that was, if I can find it, that one says, I know that the step to Catalyst 2 was a massive improvement. What is the current roadmap for Catalyst in terms of new features? So this, I kind of gave away, I guess, some of the things we're looking at. Maybe Corey can say more. And then I actually want to tie another one there, is that there's a question from an old-time collaborator who's pointing to a merge request in the GitLab that shows the GPU support. And he's asking, does this need to be merged before the GPU support can be used? So he's asking essentially what the status of GPU support is.
Great question. I'd love to know that particular merge request. I do believe that the initial offering is already there. That might be some extra piece, or I know that there was some testing cases that were needing to be merged in that might have just been labeled GPU or something. So that's kind of the state.
That person knows to get in touch with us if he wants to.
Yeah, get in touch with us later if I'd love to chat. So,
but the other question was about roadmap.
Roadmap. So then, as Berk mentioned, we have quite a bit of interest in enabling Catalyst, making Catalyst capable of saturating computational resources as best as possible, taking advantage, for instance, of GPUs if you have a CPU simulation, and vice versa, certainly vice versa with today's sort of the state of simulation at very large scales. But further than that, we have quite a bit of effort dedicated towards AI workflows. And those are specifically looking at physical modeling based on sort of data-driven pipelines. And so not necessarily things like, don't think about like LLMs or generative AI, but more sort of the data-driven machine learning approaches to improving model accuracy, et cetera. We're actually going to talk about a couple of those towards the end of the presentation. Any other questions we want to get to before we move on to the poll?
Yes, one more.
All right.
Is it possible to have interactive point of view when doing in situ without writing the data to disk after the simulation is done? By that, I mean
Yes.
simulation is done, in situ is done, and at the end of user interactively changing the camera view.
Good question.
I
So,
think he's asking about, or they are asking about live.
live. So, uh, our Catalyst Live implementation, which is the capability of connecting your simulation through Catalyst to a running ParaView client through a ParaView server, does provide you with sort of an interactive visualization of your simulation. Now, again, this kind of gets back into the sort of memory of Catalyst. This does not provide you with some sort of like grand memory of all of your simulation states, mostly because that's very memory heavy. We don't want to be saving lots and lots of time steps if we can avoid it. And so that's something that we haven't really supported in a strong way. But that state, once your simulation is done, the final state does stick around in ParaView, saved on the server memory, on the ParaView server memory. But if you want to rewind, that's not something that's exactly supported with Catalyst Live, given kind of the Live name. Let's see. Does that quite answer your question? If you're interested in sort of visualizing parts of your data after the fact, that's where data extracts, I think, are really powerful. Further, we have access to what's called cinema, which I wasn't going to talk about today, but this is a way of sort of rendering out lots and lots of views of your simulation data for sort of a quasi-interactive visualization after the fact.
Let's keep going.
All right, let's keep going. So, poll question. I think I hinted at this before. Do you leverage AI or machine learning in your simulation workflows? I'm especially interested if you are using sort of data-driven techniques for physics, but if you're using sort of large language models or sort of generative AI, I'm very interested in that as well. That's pretty cool to see, actually. I'm excited to get these numbers. Amazing. All right, so it looks like about a third of the viewers here today are using AI or ML in some capacity. That's exciting. I think so. Catalyst actually has something to offer you guys. So here we've been actually doing quite a bit of exploratory work in leveraging Catalyst to connect simulations to machine learning and AI tools directly. So the first one I want to talk about is some work out of our from our colleagues out in France in training and steering based on training and steering of surrogate models. So those of you who are familiar with surrogate models, it's sort of a representation of a solution space for a particular problem. In this particular context, they had this sort of 2D fluid flow past a cylinder, and they wanted a surrogate model that could represent velocity and time. So you could plug in velocity and time and get a simulation state from that. And so through Catalyst, they were actually able to train a surrogate model that was based on PyTorch, and then send the training state back to ParaView directly so that they could actually visualize the state and rate of training being done. But further, they actually could perform inference. So within the ParaView GUI, might be a little tricky, might be a little small on the screen here, but you could input a particular velocity value, that's an inlet velocity value, as well as a time step. And those would be sent back via Catalyst to the surrogate model, and then the solution state predicted by that surrogate model would be sent back to ParaView for visualization. So this is a really cool sort of conglomeration of tools using AI, Catalyst Live, surrogate modeling, as well as a lot of really interesting computational steering type techniques for performing this sort of surrogate modeling. And I think that Catalyst really makes this very palatable, especially for seasoned Python users. So Catalyst connects simulations directly to a Python state via ParaView Catalyst. And so from there, you have direct access to things like NumPy, PyTorch, TensorFlow, all of your favorite Python tools that are really geared towards doing this sort of work. You now have access to your simulation data as it's being environment. You can express your simulation data as NumPy arrays in a single line of code, for instance, or you can create tensors of sort of arbitrary shape and size for doing batch processing, which would be very powerful for actually performing sort of like large-scale training or large-scale inference, etc. So I wanted to talk about another use case here that we worked on with NASA as well as the University of Colorado Boulder. So here we actually used machine learning to enhance the accuracy of a Reynolds average Navier-Stokes model. So for those of you who are uninitiated to the topic of turbulence modeling, Reynolds average Navier-Stokes is a technique often referred to as RANS modeling for modeling all of the spatial and temporal scales of a turbulent flow. So here we have some flow that looks very smooth, despite being potentially a very high Reynolds number where you would expect a lot of turbulence, swirling, etc. in that particular sort of region. This technique mathematically has a term that is not closed, so we need to provide a model for that particular term. And there are decades and decades of really interesting science to actually provide a sort of model for that particular unclosed term in the math. The issue with that, though, is that all of the proposed solutions to that are deficient in some way or some form or fashion. And the goal of this project was to learn that deficiency. So how can we actually take high resolution direct numerical simulation data and inform the discrepancy between what is expected from our model and what we anticipate the actual correct value of that particular Reynolds stress tensor to be. And this is very powerful, very interesting, and we were able to actually connect this to a very mature, very high performance Fortran-based CFD simulation code. That Fortran code has decades and decades of history, but is not Python. And so actually performing these sort of AI tasks directly in the code is very challenging to impossible. And so what we were able to do was connect Catalyst via our Fortran interface directly, and then present all of the simulation data in memory to a AI inference workflow. And the results of this are actually pretty cool. So here we have RANS plus ML and sort of a roughly equivalent averaged DNS result. And in the eyeball norm, they look they have very strong correlation, which is fantastic to see. But also, I'm not going to get into a lot of the details, but the correlation between actual streamlines, et cetera, is very, very close, which is excellent to see. You want your RANS simulation to be as accurate as possible for ideally as cheap as possible as well, computationally cheap as possible. And so that's really where this is trying to fit. But with that, I wanted to, so those are kind of the cool things that we're doing in Catalyst now to make our simulations smarter. Before we move on to sort of our outro slides, Berk, are there any fun questions in the chat that we want to get to?
None that we have really time to answer. So I'm responding to those folks to reach out, or we will reach out to them. So overall, if you have a question that we were not able to answer, in all likelihood, I choose not to bring them up because they are long and we don't have time for it. Like there was a question on cinema, for example. I said we will reach out offline to those folks. And I was just typing an answer about some more advanced ways of moving data between simulation and Catalyst. And I was going to answer, look at Adios. But folks that have more questions, please feel free to reach out, and we'll do our best to answer. One thing I do want to point out, there was a thread, several people posting that they would like to see a more advanced webinar, seminar that walks one through implementing an adapter for a particular code.
Yeah.
So I'm going to answer that. One is that we have been putting some effort into creating a new website that Corey is pointing. And so there are examples there, and there's going to be more to come. We will consider the possibility of maybe doing a webinar that's more advanced that actually lets you through one of those examples, walks you through one of those examples, or maybe even just putting out a video to do that. I also would like to point out sort of the kind of following with the opening pitch is that if you want to get more support from us or you want us to work with you to implement some of the adapters, etc. There's various options. It's great. Those slides are working for what I'm saying. There are various options with which you can do that, ranging from, of course, going through this course. We can put together a Catalyst course if there's enough demand for it, a paid course, also including a paid support. But we will also try to grow the documentation as well as the content we put out there. And if people have input about what they would like to see, please let us know.
Phenomenal.
So I think that's it for the questions, Corey. If you want to wrap up, go ahead.
All right. Well, thank you all so much for coming. It was great to be able to talk about Catalyst. I know there's a bit of a high-level overview, and I'm glad to hear that there's a lot of interest in getting into some of the nitty-gritty here. Thank you so much. Again, thank you all so much for coming. Really appreciate you sticking around. And I hope to hear from you in the future. If you have any questions, please reach out. There's all kinds of ways of getting in touch with us here at Kitware. The recording of this will be on YouTube shortly after, and I believe that we'll be sending out a list of slides in a PDF form to all the attendees. So yeah, thank you so much y'all for coming. Hopefully, hope to hear more from you in the future. Great.
Thank you all.